Okay, so this is the second video for graphing for Math 60. And this one, what we're going to be doing is we're going to be taking an equation and substituting x values and getting y values out. So prior to the development of the Cartesian plane, before René Descartes started graphing things in this way, there were two separate areas of mathematics. You had algebra, which we've just talked about, where you had equations, right? And we solved these equations and got a single answer of value for x. And then mathematicians also did geometry. They worked with circles, they worked with these curves that are called parabolas. So this is the shape, if you've never thought about it, this is the shape that something takes when you throw it through the air. It follows what's called a parabolic arc. Okay? And so mathematicians worked with algebra, mathematicians worked with geometry. The Cartesian plane brought these two things together. And part of what they did was, like for instance, Galileo was working with a parabola. He would take, what he did was he would take a ball and dip it in paint and then lean a board up against the wall and roll the ball across the board, and it would make a similar shape as if you threw it through the air. Okay? And then once that's done, you can measure how far out it was versus how far down it was. And then if you go further out, you have to go further down. And he looked at the relationship between these two values. And what he found is that how far down you go is related to the square of how far over you go. Okay? So let me show you just briefly what that looks like. If we flip it right side up like this, something along these lines. Okay? This is can be described, not this one in particular, I'll redraw this so that it's more, matches up better with our formula. Our formula here says y equals x squared. So if x is 0, y is 0. If x is 1, then y is 1. If x is 2, then y is going to be 2 squared, which is 4. Okay? And you can see that this is going to continue on. And that's the shape that describes this parabola. Now, people use these a lot in application. Okay? Obviously, for things that are shot or thrown through the air, understanding the shape can help you to know where they're going to land. And in fact, this is one of the major parts of military artillery. When they shoot a missile or a rocket or a grenade through the air, it's going to follow this kind of shape, and they'll have some idea of where it's going to land. And in fact, in World War II, on the American side, they had teams of women doing calculations in Philadelphia to help the war effort. And in Germany, what was called the V-2 rocket was a kind of groundbreaking piece of military artillery where from mainland Europe, the Germans could shoot a rocket into the air with enough projectile force that it would rise up over the English Channel and then come down in London. And that was very difficult for the British to fight against. Those V-2 rockets were a very, very difficult problem for the English during World War II. So what I'm saying is that there are a lot of applications of these ideas, and they're used throughout the sciences. Okay, so what we're going to be doing in this assignment is really nothing more than making one of these tables. So let's look at problem 2 on the assignment here. And so the way we've got our table laid out is we've got x values here, -3, -2, -1, 0, and 1. And the y is going to be set equal to -3x. -3 times x. Okay, so this will be negative 3 times the x value, which is also negative 3, and so the y value there will be positive 9. And we're just going to do this for all these x values. Negative 3 times negative 2, positive 6. Negative 3 times negative 1 is positive 3. Negative 3 times 0 is 0. And negative 3 times 1 is negative 3. Now that's all I'm asking for in this assignment, and that's all that you'll see when we come to the final exam. Now, if we look forward a little bit in Math 70, what we do is we take this an extra step and we put these on the coordinate axis. Okay, let's see here. So, when x is negative 3, y is positive 9. When x is negative 2, y is positive 6. And then negative 1, positive 3, 0, 0, and 1, negative 3. And if you connect these and do it correctly, and mine's a little bit off because I was estimating, but if you connect these, it makes a straight line. And that's why these equations that we're working with are sometimes called linear equations. Okay? And these have their applications as well. Again, we'll look into that a little bit more in Math 70. For our assignment right now, all we're interested in is that you be able to accurately make one of these tables. And then in Math 70, we'll look into actually graphing them. Okay, let's look at a couple more examples here. Problem 4. We've got x's starting at negative 2, and then 0. And then positive 2, positive 4, and positive 6. And our y's are going to be equal to 1/2 x minus 1. Okay, so let's see here. So this is going to be equal to 1/2 times negative 2 minus 1. 1/2 times negative 2 is negative 1. Negative 1 minus 1 is negative 2. Here we'll do 1/2 times 0 minus 1. So that'll be 0 minus 1, which is negative 1. Here 1/2 times 2 minus 1. 1/2 times 2 is 1. Minus 1 is 0. And so on. So this will be 2 minus 1, and then here we'll get 3 minus 1 equals 2. So here are our y values that correspond to the x values. Now if you wonder why did I go by 1s here and go by 2s here, there's no real reason for that except to make the problem a little bit easier to calculate. So let's see. So what if I did 7 here? Okay. So what's going to happen here is when we do 1/2 times 7, we get 3.5 minus 1 is 2.5. So these odd numbers are going to give us fractions, which is fine. There's nothing wrong with that. If we go and plot this, let's see. Negative 2, negative 2, 0, negative 1, 2, 0, 4, 1, 6, 2. And then the 8 would give us 3, and so that 7 and 2.5 is still on there. There's nothing wrong with the fractional value. It's just a little bit trickier to calculate with. But here's all the whole number points that we were plotting, and this 7, 2.5 just falls in between those two. Okay? And there are plenty of other points on here that are not whole numbers, but again, we don't really have to worry about that. All we have to do for this assignment, take the x values, plug them in for x, and calculate a y value. Okay. Let's see here. Problem 6. So in problem 6, our x values start at negative 2, and go up by 1s up to positive 2, and our y values are equal to x minus 4. So we plug in the negative 2 for the x, and then calculate negative 2 minus 4 is negative 6, and then just continue to do that for all of these values. 2 minus 4 is negative 2. And that's all we really have to do for these problems. Okay, let's look at a couple more here. Problem 8. Let's see. X values are the same, negative 2, negative 1, 0, 1, and 2. Our y's will be 2x minus 3. So here we'll get 2 times negative 2 minus 3. So that's negative 4 minus 3, which is negative 7. Here, 2 times negative 1 minus 3. So that's negative 2 minus 3, which is negative 5. 2 times 0 minus 3. Oh, so that's 0 minus 3, which is negative 3. 2 times 1 minus 3. 2 minus 3 is negative 1. And 2 times 2 minus 3, so that's 4 minus 3, which is positive 1. And so this is what we're really interested in, is just being able to calculate those y values. Okay, we've got a couple more here to look at. Problem 10. Let's see, our x values are the same, negative 2, negative 1, 0, 1, and 2. The y values are 3x plus 2. Okay, so we're going to do the same thing that we've done on all these problems. Plug in the x values and then calculate. Negative 6 plus 2 is negative 4. Plug in the negative 1, so that'll be negative 3 plus 2 is negative 1. Plug in the 0. 0 plus 2 is 2. Plug in the 1. 3 plus 2 is 5. And then if we plug in this last value, the 2, that'll give us 6 plus 2 equals 8. And there's all the y values that we wanted to calculate. Okay. Let's see. Problem 12. I think we've got another fraction in here. So here we've got x values of negative 6, negative 3, 0, 3, and 6. And our y is 2/3 x minus 3. Okay, so again, we plug in our x value in place of the x, and then we make our calculation. Let's see. 2/3 times negative 6 should be negative 4 minus 3 is negative 7. Here, 2/3 times negative 3, that's going to be negative 2 minus 3 is negative 5. 2/3 times 0 will be 0 minus 3, negative 3. Here, 2/3 times positive 3 will be positive 2, minus 3 is negative 1. And then 2/3 times 6 minus 3, that'll be 4 minus 3, which is positive 1. You can put a plus there if you want, or leave it out, either way. And so I was going to wait until we did this second fraction problem to talk about why I changed the x's in this problem versus that problem. So if you notice, what I did here was that these x values increased by 3, which matches the denominator of the fraction that we're working with. And that's how you can get whole numbers out, okay? If you pick your x values to be multiples of this denominator, then that's a way for you to get whole number answers. And again, you don't have to do that. Now, if the problem gives you a particular set of x values, then you should use those x values. But, you know, in terms of doing this yourself, let's say if we used 5 here, this will get a little bit messy. 2/3 times 5, that's going to be 10/3 minus 3. Well, 10/3, this is 3 1/3. So if we subtract 3, we're going to come out with 1/3. And again, there's nothing wrong with that. It's just going to be in between. It'll still be on that same straight line that we would see from graphing this. It's just that it would be in between two whole numbers on the y-axis. Okay, so that's it for this assignment. Again, all we're really looking for is to take these x values, plug them in, and calculate some y values. If you have any questions about how that goes or about any of the answers, please let me know. Thanks.